Good morning. This is for the Chem 111 experiment on calorimetry. And a calorimeter is a device that's used to measure the heat flow associated with a physical or chemical process. And there's two types of calorimeters. The one that's pictured here is a bomb calorimeter. And bomb calorimeters, you're actually igniting the sample, combusting it, and measuring the heat that's given off from that. The heat comes from as you combust the sample, it goes into the surroundings here, which is the water, and that's why you have the water, the heat sink stirring, and you look for the change in temperature of the water. This is a sealed, well-insulated vessel, and it's very precise, a bit more time consuming to set up, as they tell you in your lab reading. But it's a constant volume process here, so the volume doesn't change. And in chemistry, work is always determined as pressure times change in volume. And since no volume change happens here, it's all inside this vessel, there's no work done, and it gives you an idea of the internal energy of a system. The other type of calorimeter that they use is the one that we'll be using today, is a coffee cup calorimeter, or one that's a constant pressure device rather than a constant volume. And that's what we're going to be using. And that one is basically two coffee cups nested inside each other with a lid. And what we'll have is we'll have a thermometer and the stirrer. So basically ours, as a diagram, would look like this. We'll have it covered with a lid, and we'll have our thermometer in here going through the lid, and we have a little stirrer or plunger that we use. And again, we have two coffee cups, nested, lid. And what we'll do is we'll combine our materials inside the calorimeter, and we'll stir it using the plunger, just moving it up and down, and we'll record the change in temperature. And we're going to do that for two physical processes today, and then we're also going to do it for two chemical processes. All right, so the first thing is talk about heat capacity. And the heat capacity, that's the amount of heat, if Q is the amount of heat, the heat capacity is equal to the amount of heat divided by the change in temperature. All right, this is heat capacity of a substance. So the heat capacity is the amount of heat required to change the temperature by 1 degree. And Q is the amount of heat, and T is the change in temperature. Another property is the specific heat capacity. Sometimes it's labeled C or S, and the specific heat capacity is the heat divided by the mass times the change in temperature, and this is the specific heat capacity. And this is the amount of heat that's required to change 1 gram, the temperature of 1 gram of material, by 1 degree Celsius. And that's your specific heat capacity. And we're going to actually calculate the specific heat capacity for a metal today. So that's actually part B, calculate the heat capacity of a metal. As we were saying before, that in a bomb calorimeter, it's a constant volume process, so that gives you some idea of the internal energy. And the coffee cup calorimeter is a constant pressure process. Well, it turns out that there's a quantity called the enthalpy, and that's the heat of the reaction. So Q represents heat. And so enthalpy is going to be the heat of the reaction, and that's the other thing we're going to calculate today for two reactions. We're going to calculate the change in enthalpy for acid-base reaction, and we're going to calculate the change in enthalpy for a metal acid reaction. And what we're going to do is we're going to compare the heat capacity of the metal, that physical process, or specific heat capacity of a metal, that physical process, and we can compare it to the handbook value and see how close we get. We're going to calculate the enthalpy change for an acid-base reaction, compare that to the handbook value and see how close it is. And also for the metal acid reaction, we'll see how close our experimental values correspond with the handbook value. Now, when working with the calorimeter, the heat flows from the system under study, whether it's the acid-base reaction or whether you're heating up a metal, to the surroundings. Right? And that negative sign just shows you that the heat is flowing from the hotter body to the colder body, because that heat has to be conserved. So if you write this out, no heat's lost and it all has to sum to zero. So the surroundings. The system is whatever process we're looking at, whether it's a chemical reaction or some physical process, and the surroundings, well, that's made up of the heat sink in the calorimeter, and what we typically use as the heat sink is water, because it has a high heat capacity. It can absorb quite a bit of heat. And also the calorimeter itself, the vessel. So when heat's given off by some physical process or reaction, it flows from the source into the surroundings. And the surroundings is the water, which is the heat sink, and the walls of the calorimeter itself. So we have to take into account the heat lost to the calorimeter here. So the first thing that they have you do is they're going to have you calculate the heat capacity of the calorimeter, how much heat gets lost to the calorimeter, and that's what they're doing in part A. They determine the calorimeter constant, and what the calorimeter constant is, that's the heat capacity of the calorimeter. So that's what we have to find first, and so they're actually going to do that 3 times. And the way they're going to do this is they're going to take your calorimeter, your coffee cup calorimeter, they're going to put 75 grams of hot water, and they're going to mix that with what's already in the calorimeter, which will be about 75 grams of cold water, and they're going to mix it together and record the temperature change. So there's your thermometer, and of course your stirrer to stir it and make sure it's thoroughly mixed. And how do we calculate that? All right. Well, we have 3 heat flows we have to take into account. I'm going to erase this for a second. Yes. All right, so the Q of the hot plus the heat going into the cold water plus the heat of the calorimeter all have to sum to 0. Right? Now, we talked about specific heat earlier, and we said that specific heat is equal to Q over the mass times the change in temperature. And again, that can be written as Q equals the specific heat times the change in temperature. And since they usually write it with a mass, I'll write it that way. Q equals mc delta T. And C is the specific heat. Delta T is the change in temperature and m is the mass. So what we need is substituting that equation in for the hot, we need the mass of the hot water times the specific heat of the hot water times the change in temperature. That's the final temperature of the hot minus the initial temperature of the hot. And that hot water gets mixed with cold water, so we need the mass of the cold water times the specific heat of the cold water times the change in temperature, Tf minus Ti, to show the temperature change of the cold. And also remember that we defined heat capacity as the heat flow divided by the change in temperature. Well, the heat capacity of the calorimeter, that's what we're trying to find here. So this H, the heat capacity of the calorimeter, might be labeled in some books calorimeter constant, like that. So we're trying to find the calorimeter constant times the change in temperature of the calorimeter. All of that has to sum to 0. Okay. So we have 3 Qs, and the cold water is going to be our heat sink, and the calorimeter vessel itself is all part of the surroundings. So there's our heat sink and our surroundings right there, and the hot water is going to be our source. So what we do is we'd mix these two in the calorimeter, we would start stirring, and we would record the temperature every 15 seconds until we get a stable final temperature. So if we do that, and we've got some data over here for run number 1 right there, and if we plug that information in to find our, let's find our calorimeter constant, and then we'll plug the information in. If we were solving this for our calorimeter constant, we would be solving for Ccal right here. That's what we want to solve for. And if we did that, the calorimeter constant is going to be the mass of the hot times the specific heat of the hot, change in temperature of the hot, right, plus the mass of the cold, specific heat of the cold water, times the change in temperature of the cold water. Here we are. Of course, we subtracted that all to the other side there, and all of this would be divided by the final temperature minus the initial temperature of the calorimeter. Now, since the cold water is sitting inside the calorimeter, the initial temperature of the calorimeter and the initial temperature of the cold water are going to be the same. When the hot water is added and we mix it and we get a final temperature, the final temperature of the cold, the hot, and the calorimeter should all be the same. Right? And so if we're plugging all of this in, the information that we have from that table, we have 74.8 grams as the mass of the cold, right there, we have the mass of the hot water is 75.3 right there, and we have our temperature changes. So the temperature of the cold water is going to be the same as the temperature of the initial temperature of the calorimeter. All right? And so if we put in the information that they give us, the way we would find the calorimeter constant for run number 1 is it would look like this. We've got the mass of the hot water right there is 75.3 grams. And the specific heat of the hot water. Okay, the specific heat of water is going to be the same. So the specific heat of hot and the specific heat of cold water is what, 4.184. Right? So that's going to be times 4.1 joules per gram degree Celsius. And again, that's going to be multiplied by the temperature, the final temperature of the hot water, which the final temperature is right there at 44.8 degrees Celsius. 8 degrees Celsius minus the initial temperature of the hot water, and the initial temperature of the hot water was 71.4. Remember, the hot water should lose heat, so its temperature should decrease. So the final temperature of the hot water should be less than the initial temperature. So there we are. And then, now, looking at the cold water, the mass of the cold water that we used was 74.8. 74.8 grams. And again, the specific heat of the cold water is the same, 4.184 joules per gram degree Celsius. And the change in temperature now is going to be, well, the final temperature of the cold water, well, that's 44.8. They also have the same final temperature. And the initial temperature of the cold water was 21.6. And that's everything in the numerator. And then the change in temperature of the calorimeter is going to be the same as the change in temperature of the cold water there, right? Because the cold water was sitting inside the calorimeter. So the final temperature of the calorimeter is going to rise up to 44.8 degrees Celsius, and it started at 21.6 degrees Celsius. There we go. And what will happen is our units will cancel out, and we'll be left with a value in joules per degree Celsius. And when they were doing this experiment, there was actually a spreadsheet that they used, and this is the spreadsheet. And when you look at the spreadsheet, here in experiment 1, run 1, they have these values put in here, and what they've got is they have the calorimeter constant calculated right there as 48.2177 or 48.2 joules per degree Celsius. So that should come out to be 48.2 joules per degree Celsius. And that's the heat loss to the calorimeter, and that's characteristic of the calorimeter that you use. So if you were doing a calorimetry experiment, the first thing you'd have to do is find out the calorimeter constant for your calorimeter. And that's what we're doing there, because we're going to need this in parts B, C, and D. So if you are plugging in the information that they gave you into the spreadsheet, they would find your calorimeter constant. And they did the run 3 times so that you could get a good value for that calorimeter constant. And if we were plugging that in, and they had in run number 2, they had what, 75.3, 21.8, they had some, sorry, 21.8. So what we'll do is just plug this in right here, 74.5 and 70.8 and 45.4. And they also had some information on run number 3, where they start with 75 grams of the cold water. The initial temperature of the cold water was 22.4, and it was 75.73 was the mass of the hot water. And again, the temperature 69.2. I'm just typing all this in, was the temperature of the hot water, and 44. And the reason I'm typing all this in is to see how close they were each time in determining their calorimeter constant. Now, if we look over here, oops, there's a mistake typed in there. Can't type that. Temperature was 22.4 and it should be 75.73. 75.73 rather than a T. And let's see how close the calorimeter constant came out to be. And here in run number 1 they got 48 joules per degree Celsius, and run number 2 they had 20 joules per degree Celsius, and in run number 3 they had 55.8 joules per degree Celsius. So the calorimeter constant between those runs, it looks like runs 1 and 3 were closer than run 2. So they get since this part's a little bit tricky here, they try and get a good average calorimeter constant. So if you were doing this in lab, you'd want your runs to be as close together. Whatever happened there on run number 2, maybe they didn't wait long enough to get a good final temperature reading. As remember, they have you record the temperature every 15 seconds until you get a stable temperature, and also mixing it the same way each time to reach that final stable temperature. So they take that average calorimeter constant, and then that gets used in the rest of the lab. So with that, you can actually find out the specific heat capacity of a metal, and the 2 metals that they use are aluminum and zinc. And then once you find that heat capacity of the metal, you can actually go and look that up. So the way you would find the heat capacity of the metal is you would heat up a sample of aluminum pellets, and those aluminum pellets would actually be in a test tube, and you would put it in a hot water bath. And so you would measure the temperature of that hot water bath, and that would be your initial temperature of your aluminum pellets. Then you would take those aluminum pellets in the test tube and you would put that into your calorimeter, which would be filled with a known amount of water. And then you would record the temperature. So in this one, let's erase this, you would take heated aluminum pellets. So you'd have a test tube, you'd have a test tube, and you'd have your pellets in it like this along the bottom, and these would have been heated in a water bath, and you'd measure the temperature of that water bath, and that'd be your initial temperature of your pellets. As I said, you put that in the calorimeter and then mix it and record the final temperature. So how do we record the specific heat of the, how do we calculate the specific heat of the metal? Well, now that we know our calorimeter constant, we can. And so for this one, the specific heat of the metal, we're going to have our three sources, or three heat flows again. And at this time, for specific heat of the metal, we're going to have the heat associated with the metal plus the heat of the associated with the water plus the heat associated with the calorimeter. All of that has to sum to 0. And now, how do we find this? Well, if we put in what we know, the heat of the metal is the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal plus the mass of the water times the specific heat of the water, we know that, times the change in temperature of the water. And now we have the calorimeter constant. We know that we have a good average calorimeter constant, and we need the change in temperature of the calorimeter, which is going to be the same as the change in temperature of the water. All of that will have to sum to 0. And what we're solving for is the specific heat of the metal. We know the mass of the metal, we know the change in temperature, we know the mass of the water, we know the specific heat of the water, we know the change in temperature of the water, we know the heat capacity of the calorimeter, and we'll know the change in temperature of the calorimeter. So it's just a matter of solving for the specific heat. Now, what's our heat capacity of our calorimeter? We'll go back to our spreadsheet here. And we know that the heat capacity of the calorimeter, the average is 41.47 or 41.5 joules. So that's where we would get that information. So this would be, we'll say 41.5 joules per degree Celsius. So, putting in what we know, the information given, the mass of the metal, the hot metal, is 50.4 grams right here. So 50.4 grams. The specific heat of the metal, we don't know, and that's what we're solving for. And the change in temperature of the metal is going to be, the temperature of the hot metal, that's going to be the initial one, 100.2. And the final temperature is going to be 30.4. That's degrees Celsius. Sorry, there we go. And the mass of the water, that's the heat sink there, 74.7 grams. The specific heat of the water is 4.184 joules per gram degrees Celsius. And the change in temperature of the water, well, the final temperature is going to be 30.4. And the initial temperature, right off the table here, is going to be the 21.8 degrees. There you are. And then the heat capacity of our calorimeter, that's the 41.5 that was calculated in the first part, joules per degree Celsius, times the change in temperature of the calorimeter. That's going to be the same as the change in temperature of the cold water, since the two sit together. Again, all of that has to equal 0. And then you would solve for the specific heat of the metal. And if you did that, you'll get the specific heat. And again, this was for the aluminum, but the specific heat would be and that is the 70.47 grams, the 4.184 joules per gram degree Celsius, times that change in temperature for the water in the calorimeter, and the heat loss to the calorimeter here, it's the calorimeter constant times change in temperature, the calorimeter. Oops. Write that a little better. And put the last closing bracket there. Again, all of this would be divided by the 50.4 grams times the change in temperature that was of the metal, change in temperature of the metal there. Again, the metal was the source of our heat, so the temperature should, the final temperature should be less than the initial temperature. And so if you did that, and you plugged all that information in, and if we plug that information in there to specific heat, and we had the mass of the cold water as 74.7, the temperature of the cold water initially was the, what was that, 21.8, and the mass of the hot metal was 50, 50.4. Temperature of the hot metal initially was 100.2, and then it decreased to 30.4 there. And so if you did that, you get a specific heat capacity for aluminum of 0.864 joules per gram degree Celsius. And that's the specific heat capacity calculated for aluminum. And if you were to look that up, and I'm sorry I did not look that up, I will look that up right now. Have a quick look. Heat capacity of aluminum. Heat capacity of aluminum, do they actually give this quickly? So for heat capacity, periodic table, there we go. And find it for aluminum. They list the specific heat as 0.9 joules per gram Kelvin. Yes, we did ours in degrees Celsius. But one thing, if you're calculating the change in temperature, if you're calculating the change in degrees Celsius, or you're calculating the change in degrees Kelvin, it would be the same as long as you're consistent in your units. Because if my change in degrees Celsius, right here, if I went from 30 to 21, roughly a 9-degree change in degrees Celsius, that'd be the same in Kelvin, 9 degrees if I was doing this in Kelvin. All right, but I have to be consistent in my temperature units in all of my terms here. So they're giving it in Kelvin, and it's 0.9, and we have 0.8 in degrees Celsius. So yes, we're close, because that would be the same if it was in degrees Celsius. And you could prove that by doing the conversions from Celsius to Kelvin. So yep, we're actually very close at 0.86, and they're listing it as 0.9. So that was pretty good. So that's the specific heat capacity of a metal. The next thing is we're going to do it for a chemical process now, and we're going to calculate the enthalpy change for a magnesium acid reaction. So how do we calculate the enthalpy? I'm sorry, we're going to calculate it for an acid-base reaction first. So how do we do that? Well, in this one, what you're going to do in your calorimeter is you're going to mix an acid, a strong acid, and a strong base at 1 molar concentrations of each. And you're going to calculate the heat associated with that reaction. So if we were determining the heat associated with that reaction, we would write our 3 Qs. There is some stray marks here. If we determine the heat associated with that reaction, we have the heat coming from the reaction, going to the heat sink, which is water, going into the calorimeter. Now, for this reaction, since it's a strong acid, strong base, and what we're doing is we're mixing HCl together with NaOH, and we're getting a salt and water, NaCl plus H2O. The net ionic reaction here is just hydrogen ions plus hydroxide ions going to water. All the other ions in solution, like sodium and chloride, they're spectator ions. So really, this is the overall reaction for any strong acid base. Okay, so that's the net ionic reaction, and that's what we're determining really the heat of reaction for here. Now, what we're doing in this particular case in our calorimeter is, if we had our coffee cup calorimeter, we would have one of the reactants, like the base, we would put that right in here. We'd have a known mass and we have a concentration. We want to use the same concentrations. So we might have in there about 75 grams of NaOH. And then what we'll do is we're going to add 1 molar, 75 grams of HCl. Again, we have our lid with our thermometer and our stirrer right there. And so what we do is we add the acid. We'll have the initial temperature of the acid before we add it. We'll have initial temperature of the base before we add it. Then we add our acid and we mix it and we record the final temperature. And what we're solving for in this one is the heat of the reaction. So that's what we're solving for here. And in this particular one, everything's occurring right there in the calorimeter. So the water that's formed here. So this one, the way we'll find our heat of reaction is that's going to be minus Q for the water that's formed to the calorimeter. So everything goes right here into the surroundings, comes from the reaction straight into the surroundings. So what we have for water, or the heat sink here, is consisting of the combined acid and the base together. All right, so reaction took place right here in the heat sink. So what we'll have is we will have the mass of the solution times the specific heat of that solution. All right, and that's really the water here. So I'll put a little W under that. Times the change in temperature of that solution. So TF minus Ti. And of course we got the heat capacity of the calorimeter constant, times the change in temperature of the calorimeter. That's Tf minus Ti. And the change in temperature of that calorimeter is the same as the solution that's in there. And all of that will be our heat of reaction. So if we're putting in the information that they gave us, what this means is we started with 75.2 grams of acid, because the acid and base react together to form our solution in water. It's aqueous solution. And we're adding that with, and if we look at the chart, the data table here, the mass of the base was 75 grams of base. And the solution, the specific heat of the solution, well, it's an aqueous solution, it's water, so that's going to be 4.184 joules per gram degree Celsius, because that really is the overall net reaction forming water, and that's the specific heat of our solution. So the solution in our calorimeter is our heat sink in this case, and the change in temperature is, well, they give the change in temperature as 22.2 degrees Celsius initially, and then it rose up to 28.2. So the initial temperature was 22.2 and the final temperature was 28.2. So 28.2 degrees Celsius minus 22.2 degrees Celsius. So that's the heat associated with the solution that was formed in the calorimeter. And how much was lost to the calorimeter? Well, that's the 45.04 joules, was it? 45, oops, sorry, I didn't mean that was the 41.5. 41.5 joules per degree Celsius times change in temperature, which is the same as the change in temperature of the solution. Close bracket, close there. And that, and that is going to be your heat of reaction, right? And remember, the enthalpy is the heat of reaction. So whatever that turns out to be, if we plug that into a spreadsheet, quickly to find out here, if we were doing this, the mass of the acid was 75.2. The mass of the base was 75. The initial temperature was 22.2. And the final temperature was 28.2. And from that, they get the enthalpy, or the heat of reaction, as right there. They've got it as, oops, I'm sorry, minus 4,015 joules. They've got that as minus 4,015.89 joules, or 4,015 joules right there. So when units cancel out, you should be left with joules. and you can convert that to kilojoules. It's minus 4.015 kilojoules. And that is the enthalpy for an acid-base reaction. And what they were doing in this experiment was they actually had you do it for two different acids and bases. And they had you do it in the first one for HCl and NaOH, and then they had you do it a second time using HCl and potassium hydroxide. And that was to show you it didn't matter what the identity of the strong acid, strong base was, the net reaction for any strong acid, strong base reaction is always going to be the same. That's hydrogen ions and hydroxide ions coming together to form water. The last one that they have you do is calculate the enthalpy for a metal acid reaction here. So in this one, what we're going to do is we're going to have a mass of metal and we're going to add it to a particular acid like HCl. So you'll take some metal like magnesium, and in your calorimeter you will have some strong acid sitting in there, and calorimeter you would have inside it acid solution, and you'd have about 150 grams of acid, maybe like HCl in there. And then what you would do is you would add about half a gram of your metal like magnesium, and just like before, record the temperature as you stir for 15 seconds. Record the temperature every 15 seconds as you stir the solution, and get a final stable temperature reading. And for this one, it's done similarly. You have the mass, the heat of the reaction, plus the heat sink is going to be that solution formed, plus the heat going to the calorimeter. And that solution that is formed is mostly water, so like we did before, you'll use the heat capacity of water there. So heat of the reaction is delta H. That's the enthalpy, just like up here. And I should write that to be consistent. So for this one, if we were to find the heat of the reaction for a metal acid reaction, what we're doing is we're combining magnesium solid plus hydrochloric acid solution, and we're going to get magnesium chloride in solution plus H2 gas. So it will bubble out. Alright, and so that is the reaction that we're carrying out in solution. And what's basically happened is we get magnesium, H plus, magnesium 2 plus, H2, that. Right, the chloride is just a spectator in the reaction. And we calculate this. We're going to find the heat of the reaction just like we did before. The heat of the reaction, or the delta H, is going to be, whoops, the heat associated with the solution that's formed plus the heat going to the calorimeter there. And if we did that, plugging in what we know, that's the mass of the solution times the specific heat of the solution times change in temperature of the solution plus the specific heat of the calorimeter. I'm sorry, the heat capacity of the calorimeter, not the specific heat because we don't weigh the calorimeter, times change in temperature of the calorimeter. Right, and again we have to take the negative of all that because we subtracted it from one side to the other. And if we put in what we know, the values, the masses of our solution, well, we had 0.5 and 150. What did we actually use? They actually used 0.41 grams of magnesium and 150 grams of acid. So that would be 0.4 grams plus 150 grams of HCl multiplied by the specific heat of the solution. Well, the solution is water. This was all in aqueous solution. So that would be times 4.184 joules per gram degree Celsius times the change in temperature. Well, change in temperature that they got, if we look back up here, the initial temperature was 22.4 and it rose to a final temperature of 34.4. So it went to 34.4 degrees Celsius from 22.4 degrees Celsius. Right. And again, the heat capacity of our calorimeter was 41.5 joules per degree Celsius, and the change in temperature will be the same as the change in temperature of that heat sink, 34.4 degrees Celsius minus 22.4 degrees Celsius. And that, if we do that, that will give us the heat of reaction for the magnesium combined with the hydrochloric acid. And so, if we plug that information into the spreadsheet that they gave us, the initial temperature, the mass of the acid was 150 grams, and the initial temperature was 22.2, was it? 22.4, sorry. 22.4. The mass of the magnesium was 0.41. And the final temperature was 34.4, I believe. Make sure I get that right. 34.4. And if you do that, it gives you the enthalpy change right here as 47,000. Oh, that's awful. Kind of large there. Doesn't make any sense. Let's see. They've got it as in kilojoules per mole. I'm sorry. This is the one we're looking for right here. That's what happens if you convert it into moles of magnesium and calculate it. Let me erase that mark right there. So there's our enthalpy change in joules, and that's minus 8,042 joules. joules right there. So that's our heat of reaction, and it's exothermic, of course, because of the sign showing that we're giving off heat. If it was endothermic, it would be a positive sign. So that's our joules for the metal acid reaction. And that's an example of how you calculate the heats of reaction associated with two chemical processes, and how to calculate the specific heat of a metal, and also to find the calorimeter constant. So if you're doing a calorimetry experiment, the first thing you have to do is find the calorimeter constant, and then you would use that in the rest of your calculations. So in this particular lab, there's actually a simulation in McGraw-Hill Connect, and you'll actually carry out that simulation, and it should be close to what we're doing right here. This is actually the lab that you would have done in class, and knowing how to do these calorimetry calculations, that's what you'll need to know for the lab practical. Anyway, if you have any questions, please contact me by email. Unfortunately, I can't be in class today, but if you contact me by email and you even want to schedule a time, I'll be happy to meet, WebEx meeting, and I will try and have another time here available tomorrow if you're able to meet. Like I said, I'm always here between 7 and 2:30, so please let me know what's convenient and I'll be happy to help. Thank you very much.